In today's class, we will see some of the applications of Gauss law. We will see one through an example. So this is to find out the electric field outside a spherical shell using Gauss law. So first let me give you the question. Using Gauss law, obtain the expression for electric field due to uniformly charged spherical shell. Of radius r at a point outside the shell. Draw a graph showing the variation of electric field. Draw a graph showing the variation of electric field with r. Variation of electric field with r, small r, for r greater than capital R and r less than capital R. So here small r is some r, the value changes, so you have to show the graph for r greater than the radius and less than the radius. So using Gauss law, obtain the expression for electric field due to uniformly charged spherical shell of radius r at a point outside the shell. Draw a graph showing the variation of electric field with r for r greater than r and r less than r. We will see the solution. Now we will consider a uniformly charged spherical shell, and let us assume plus q is uniformly distributed over a spherical shell of radius r. Let us consider charge plus q is uniformly distributed over a spherical shell of radius capital R. We need to find out the electric field E at some point which is lying outside the shell. Let E is to be obtained at point P which lies outside the spherical shell. Now, so consider a spherical shell. Now we have assumed that the charge plus q is distributed uniformly. So charge plus q. Let the center point is O, and the radius of the sphere is given, that is R. Capital R is the radius of the sphere. We need to find out the electric field at some point P which lies outside the sphere. So the electric field due to these plus charges are radially outward, and the electric field will have same value at all the points which are at equal distance from the center O. So therefore we can consider a spherical Gaussian surface. So now consider a spherical Gaussian surface. So I will take, at point P we need to find out the, so let me say this is the point P where I need to find out the electric field. Let us say it is at a distance small r. The center. So because it is a positive charge, the electric field is radially outward. Similarly, if you consider a small area ds, the area vector will also be along E only. So if I consider a small area here, the area vector will also be along ds, will be along E. So the angle between E and ds will be 0. This is ds. So here you can write this is a Gaussian surface, and this is charged spherical shell. Charged spherical shell. So E, the electric field at any point is radially outward. E at any point is radially outward. This is radially outward because it is positive charge and has same magnitude at all points which lie at the same distance r from the center, same distance r from the center of the spherical shell. Center of shell such that r is greater than r. So therefore Gaussian surface is a concentric sphere of radius r such that r is greater than capital R. Now by Gauss theorem, by Gauss law we have so the electric field, line integral of electric field, surface integral of electric field is q by epsilon naught. Total flux through the Gaussian surface is given by q by epsilon naught. And we know the angle between E and ds are parallel to each other. So angle between E and ds is 0. So this is actually vector. So therefore integral of E ds cos 0 is equal to q by epsilon naught. Cos 0 is 1. So E into surface integral of sphere is equal to q by epsilon naught, or the area of spherical shell is 4 pi r square. Equal to q by epsilon naught. Or I can write the electric field E is one by 4 pi epsilon naught into q by r square. So this is electric field outside the shell. So E is 1 by 4 pi epsilon naught into q by r square. Remember here angle between E and ds is 0 because E and ds are along the same direction. And the magnitude of E is same at every point on the Gaussian surface. So we can write the surface area as area of the sphere, that is 4 pi r square. So the electric field which we get outside the shell is 1 by 4 pi epsilon naught into q by r square. The second question says draw the graph showing the variation of electric field with respect to r for r greater than 0 and r less than 0. So the second question is about E versus R graph. Now when you consider the spherical shell, so we have calculated the electric field outside the shell. Now what is the electric field inside the shell? So for R less than capital R, that means, so this is capital R, the radius of the sphere. So if you want to calculate inside a spherical shell, consider a Gaussian surface which has a radius of R and lies inside the sphere. Now in this case, field inside the shell, so there is no charge inside the Gaussian surface. So charge enclosed by Gaussian surface is 0. So this is the Gaussian surface. Therefore, E into 4 pi r square equal to 0, or electric field inside the shell is 0. So remember, the electric field inside a uniformly charged spherical shell is 0. Now we can easily draw the graph. Consider a shell which has center at O. This is our x-axis, and in the y-axis we have E. So up to this point, up to R, so this is the radius R, capital R is here. Up to R, the electric field is 0. Electric field inside the shell is 0. Up to this point, E is 0. And on the shell, it is 1 by 4 pi epsilon naught into Q by R square, for R equal to R. So at this point, A is 1 by 4 pi epsilon naught into Q by R square. And then as R increases, E will reduce. So this, in this case, E is 1 by 4 pi epsilon naught into Q by R square, or E is proportional to 1 by R square. You can write, okay, Q by R square. So inside the shell it is 0. On the surface of the sphere it is 1 by or 4 pi epsilon naught into Q by capital R square, where R is the radius of the sphere, and then it exponentially reduces, with respect to R. So this is a variation of E with R. So this graph shows variation of E with R for R less than R and R greater than R.